Welcome everyone to this session. I'm Daehyeok Kim. I'm a senior researcher at Microsoft. As many of you probably know, SONiC is one of the popular network operating systems, which is mainly used for managing hardware switches. So recently, there's a new branch of SONiC called Disaggregated APIs for SONiC host or Dash, which is developed for managing data planes at the edge, such as smart NICs and software switches. In this talk, Reshma Sudarshan, who is the Director of Application Engineering from Intel, and Sommers, who is a Senior Software Architect from Keysight Technologies, will be talking about how to leverage P4 to specify Dash overlay data planes and its use cases. Reshma and Chris, the floor is yours.
Thank you, Daehyeok. As Daehyeok was mentioning, SONiC is the mainstream open source network operating system that runs on switches in cloud and enterprise data centers and is currently being extended to support additional network devices such as smart NIC with the new Dash initiative. As the packet transformations happen within each device in the network from edge to cloud, SONiC with the new Dash extensions will be capable of managing both the software and hardware components in these devices. Dash itself aims to curate the inner workings of the edge device, accurately defining the pipeline to realize the cloud service scenarios, and with the goal to optimize performance to achieve 10x or even 100x stateful connection performance. Dash extends the SONiC and SI objects to describe additional network services for the cloud, including the 7 initial services listed on the top right-hand side. The use case currently under discussion as a starting point for Dash design is the VNet to VNet use case, and this involves overlay features such as connection tracking to be supported in a Dash device like IPU. And I will go into these details of how it can be implemented using P4. I will also go over the load balancer service used in conjunction with connection tracking, and also touch upon the encryption decryption service requirements and how that can be done in P4 as well. P4 itself can be used to describe, as we know, the packet transformations that occur in each network element in a cloud data center for a packet that enters a pipeline anywhere in a data center. P4 is able to give the network operator a complete picture of the network, allows for models to be built and tests written to validate the network configurations and look for escapes. Even fixed function devices in the network could be modeled in P4 for completeness. Once a network operator has the P4s put together as one complete Uber P4, the control plane code to manage and orchestrate the entire network can be auto-generated with tools. Visibility in the network improves dramatically due to the complete description. It's possible to allow tap points in the network on demand to audit, inspect traffic for correctness. PNA, the portable NIC architecture, is designed to model common features of broad class of network interface card devices by providing standard APIs and coding guidelines to enable developers to write programs that are portable across multiple NIC devices that are conformant to PNA. Connection tracking is a feature in data plane that is used to keep track of individual flows and allow for stateful operation of the flows. Optimal management of large number of flows with primary focus on CPS performance, connections per second. This involves the ability to add new flow entries to a cache in fast path without involving the control plane. Using the new P4 construct called add-on miss, this table is allowed to add a new entry in the flow cache on a miss after a flow 5-tuple lookup of the flow. So this flow cache now becomes a stateful connection table where there is per entry tracking, and these flows are now time-based. When the rule is added to the stateful table, it is allowed for some duration, and we can perform other checks based on the flow state. If a SYN, for example, comes in and we have already a flow that is in established state, we need to take corresponding actions and possibly even mirror a packet to the control plane to inform. And likewise, just like add-on miss, it is possible to age and delete the entries in the packets per second line rate that we support, and have multiple values for the timers for each flow entry based on profiles. I will talk a little bit about layer 4 load balancing and go into the stateful firewall. Load balancing, as we know, is a feature that switches traffic from using VIP to VIP connectivity, which involves transiting server load balancer muxes, into using direct path between VMs eventually. Since the service endpoints are spread around across in the data center for a given service, with SDN, we will be able to control where all the services can run and then inform the nodes in the data center as to what the options are for the possible backends. In load balancer application, when an application requests a service based on a service IP, and if the node has been programmed by a SDN controller, it knows what are the backend IPs that can service this request, and also help pick one from the pool. SDN-based load balancing can help with load placement for a service and controls the need to spawn more backends for a service to scale up or down based on current demand. Coming to stateful firewall, it goes in conjunction with the connection tracking feature that we have been discussing. The stateless firewall rules uses static policies, and they can be in different types of tables like exact match, LPM, or range checker port range. And that can be without any time boundaries or stateful elements in it. But the lookup then determines which flows are going to be allowed to be added into the flow cache, which will be a stateful table. Once the stateless firewall rules deem the flow is allowed, then the hardware adds to the stateful connection flow table. Stateless policy allows that for each flow from the trusted direction, like a server, in case of asymmetric firewall scenario. And then the entry is auto added into the table using the add-on miss feature that we just discussed. There's a concept of trusted direction, as I talked about in the asymmetric firewall, and also in the other case, which we have been discussing in the Dash community, which is the bump in the wire use case with VNet to VNet scenario. Once the stateless policies allow, we are able to, at that point, add the individual flow rules and that are going to be time-based and allowed for a duration. The other checks involve include SYN packet coming in when the state is already established, or if there is a packet that comes where we monitor the sequence number and ensure it is neither stale or not too far out in the future, and we are going to be able to detect the attack and drop the packet. Now going into a new use case to allow for security in the edge devices. One of the 7 Dash scenarios is the encryption service as well. And I just want to show how even this can be described using P4. In PNA, we have a concept of mini parser, which is written by the control plane, and in P4, which can determine the presence of an IPsec tunnel using ESP header. This lookup itself could have other entropy values like source IP, destination IP, and then with the ESP header yields the corresponding security association index. This is passed to an inline extern to decrypt the packet based on the RFC algorithms, decryption algorithms, and the rest of the packet is sent to the main parser to continue regular packet processing and further possibly add different NCAP at the egress as well. Intel is involved in contributions to the IPsec area, and we want to add the IPsec feature, which is applicable both to SONiC as well as Dash. In this process, we plan to add a new IPsec container and also integrate a third-party IKE Exchange application called StrongSwan. We add a backend plugin that will eventually interface with the Redis DB within SONiC and be able to program all the hardware entries, including the security association. When we talk about Softswitch, it is a more complex Dash device as compared to an appliance with one or more NICs in a server. It could seem like it assumes a role of a switch and offloads server functionality via SmartNIC by keeping the existing server infrastructure and augment it with high-density flow tables handled optimally by SmartNICs. The key here is that with a combination of functionality coming from switch NPU, which is involved in the device, as well as the NIC IPU functionalities, like the large-scale flow connection tracking that we discussed. If both these devices, that is NIC and switch, are P4 programmable, we have a very good way of creating this complex device, such as Softswitch. At Intel, we are also working on a Softswitch running SONiC stack on a server using the P4 DPDK pipeline, which is a P4 programmable DPDK and is performant. It also adheres to the latest PNA standard that we discussed. It is a good vehicle for left shift for development and helps get framework all ready and with P4 DPDK as a pipeline in the host, allowing us to use the same software stack for both Softswitch as well as hardware. Intel also has developed PSI-PTF test harness and has upstreamed it to OCP PSI. This is an auto-generated Python-based data plane testing framework. And for Dash, we are in the process of adapting this framework to work on Dash devices, which uses fewer number of ports. And the underlay test cases as well will be adapted to the new Dash devices requirements, as well as the use cases, including underlay as well as overlay. And here Intel is collaborating with Keysight on this effort. And Chris will talk more about this and also the addition of Dash overlay test cases in this new test harness as well. Chris, over to you.
Thanks, Reshma. Thanks for the intro and the segue. First, I'd like to introduce Keysight in case people aren't familiar with Keysight. We're a very well-known electronic test and measurement company. We've been around for decades and we test virtually everything electronic. But we're also well-known in the SONiC community. We do test bed development, test cases. We contribute to the working groups and also push upstream commits to GitHub. And our Ixia brand traffic generators are pretty well known in the networking industry. So we're going to leverage all this expertise in the SONiC Dash project. I'd like to explain some of the overarching test objectives. First of all, as Reshma mentioned, we have to add stateful testing to the existing stateless tests that SONiC already has. So besides layer 2 and 3 stream testing, we need to test stateful connection tracking, etc. We need to test both performance and conformance. Performance might include measuring absolute throughput, connections per second, etc. Conformance thoroughly tests APIs and functions, not necessarily under speed conditions, but thoroughness is important. We're going to use P4 to model the data plane traffic, but it also generates the switch abstraction interface, which is the API control plane for the data plane. We're going to test multiple API layers in the SONiC stack, not only at the data plane interface, but all the way up to the northbound SDN interface. We'd like to use the same functional tests over and over for both software implementations to verify the P4 model, which can run in a server. And we also want to verify at line rate all of the hardware implementations. We'd like to use the same tests for both so that we don't have to redo our work and we can cross-check everything. We want to automate everything inside of a CI/CD pipeline for regression testing. So for example, anytime the code changes, it gets automatically retested right away. And finally, we want to create a framework where everyone can contribute test cases. So we'll seed the repo with exemplary test cases for all the different areas. and hopefully people can step in and add test cases by just following the examples. This diagram shows one view of the workflows for test case generation and running. Let's start over here with the P4 code that describes the data plane. It's a source of truth for many things. It defines the data plane behavior itself, packets in and packets out, which we will actually run on P4 targets in software. It generates the SI headers, which becomes the data plane abstraction programming interface. And even beyond that, it generates a SciThrift test harness, which we can use to exercise the devices. We can run Python scripts, which exercise the Python client library to program the device under test. We can also use these scripts to program software and hardware traffic generators, which will send packets into the devices. The primary goal is to test hardware devices, SmartNICs, IPUs, and DPUs. We will test these with test cases that are stored in the repo. And bear in mind, these devices don't necessarily execute P4 code natively. Some of them do, some of them don't. But the P4 model is still a source of truth for how this should behave. So if you configure it a certain way and send it packets, you should get an expected response. We've also tested the reference model inside pure software using software traffic generators. These are connected in software using virtual Ethernet bridges. And we want to reuse these tests for all the different interface layers, which I'll show next. The software and the hardware, they should both pass the same test, at least functionally, not at performance though, because hardware runs much faster than software. If everything is working correctly, then all the software targets and all the hardware targets should agree at their interfaces. This shows some of the different layers in the SONiC stack. People who are familiar with SONiC will recognize a lot of this. There's some new elements, including the Dash orchestration agent and the GNMI client, which is the SDN interface. That's new for SONiC in terms of the Dash program. I want to show how one set of test cases can exercise all the layers in this stack. We start with a common set of test cases where the device configuration is stored in some intermediate format that's neutral, such as a JSON configuration. And we're going to write some test cases that apply these configurations at the different interface levels. We'll start from the bottom up and program our device using the Dash API, using the SciThrift framework. So that verifies, this is basically the fundamental contract that the different DPU vendors need to implement. So SmartNICs, DPUs, and IPUs will all agree at this boundary. Once that's done, it can be integrated into the entire SONiC stack. The next level we would want to test is the Redis interface into the Redis database. This is the middleware and plumbing and persistent store for SONiC. It's also a pub sub mechanism so that when you make a database entry here, it gets propagated down to the device. The next level we would test is the outermost, which is the SDN controller interface. This uses GNMI. Now, this schema is specified in Yang, and the interface is GNMI, which is another gRPC transport. However, the objects that get programmed at this level propagate down and get turned into Redis database objects and ultimately get programmed at the Sci interface. All these operations are semantically equivalent. So we should be able to write one test case that then gets transformed through an appropriate driver to test all of these layers. And that way we can test functional equivalence at every level and reduce our work and also ensure that everything's working properly in lockstep, no matter what change is made. Now I'd like to talk a little bit about software testing. We talked about testing the P4 reference model in software. We're using two approaches. One is using the behavioral model V2, which is very popular in the P4 community. And it's being modified and enhanced by the community to add stateful services and features like connection tracking, add-on miss, etc. This effort is ongoing. And by running this in a server, we can run the reference P4 code and program it using SciThrift through this stack. There's a SciThrift server, which we discussed, a libsci wrapper interface, an adapter to P4 runtime, and that ultimately programs the P4 runtime server and behavioral model with a configuration. This is actually already up and running in the Dash repo, and it's just getting going where we're going to be able to program it through Scythrift in the near future. So we will apply test cases to this software engine and send traffic to it using virtual Ethernet connections. Similarly, the P4 DPDK implementation, which Intel is spearheading, this is a commercial grade, highly performant implementation. It's more than just a simulator. It's actually, this is commercial quality that can be used in edge use cases. It's also going to execute the P4 reference code, and we can also send traffic to it through virtual Ethernet interfaces. Actually, you can hook this up to a NIC device and send traffic through physical ports as well. There's a variety of traffic generator approaches, which I will discuss shortly. But in summary, we're going to be testing the BMV2 first, and this will be run in the cloud under CI/CD control so that any changes that get made can be tested immediately. And likewise, we'll progress to the P4 DPDK implementation for performance testing, where we can run tests much faster with high rate flows. And I'll talk about traffic generators. Traditionally, PTF has been used in the P4 universe. It's very popular, and you'll see it in all the P4 tutorials. You'll see it in vendor software distributions, and it's also prevalent in the SONiC management testbed. PTF is really popular and has a lot of test cases. It's easy to use, but it is a software traffic generator, and it's primarily for functional testing, sending a few packets at a time to verify inputs and outputs. And there's no real path to go to line rate support. So if you want to test a device at line rate, like hundreds of gigabits per second, SCAPI isn't really capable of doing that. So Keysight has been developing a new framework, which we call Snappy and Open Traffic Generator. It also has Python and Golang bindings. It's a very easy to use library. But what's really exciting is that you can write the same test to run both in software and hardware. So we have implementations in Docker containers that can run at tens and tens of gigabits per second. And you can go all the way up to hardware line rates, up to 800 gigabits per second in a box. So by using this same library across software and hardware, we can scale to line rate, write one set of scripts that can test everything from DC to daylight. And I encourage you to follow these links to learn more. I did talk about this framework last year at the workshop. So in conclusion, we showed how P4 can be used to model all the Dash services. Reshma did a nice job covering that. And not only can we use P4 to model it, we can actually execute P4 on software switches and some hardware devices. Also, P4 can model the behavior of the data plane on devices that don't even use P4, because P4 is a great modeling language as well. We're also using the P4 to generate the programmatic API using Psi, and also it can generate the Scythrift test harness. So we really have a single source of truth that generates not only the implementation, the reference model, and even the test framework. We're going to use declarative test cases to exercise multiple device types and multiple software APIs. And finally, we're going to extend the classic Scythrift tests with Snappy-based tests to handle slow and fast traffic with the same scripts. So thank you very much for listening, and I'd like to show a call to action. There are many open source communities and projects that have been referenced in this talk, and you're welcome to investigate all of them and join to just listen and learn or contribute. And there's a few extra links to follow if you're interested. Thank you very much.
Great. Thank you for your talk. This is very interesting and practical idea and tool. So I have some questions regarding the concept of Dash and the roles of P4 in this context. So the first question is, what's the key functionality that Dash provides on top of the original SONiC? I think this would be helpful, especially who are not familiar with SONiC in general.
Reshma, do you want to handle that?
Yeah, sure. I'll take the first pass. Dash adds a few more set of use cases that on top of the switch use cases that we have seen so far, which is mostly underlay use cases. For example, LPM lookup or route lookup or ACL or VXLAN, for example. Now, Dash talks about the optimal TCP flow management using connection tracking and stateful connection tracking and optimizing the performance there. So the features like add-on miss, it's a new concept and drives majority of how the flows are handled and how the flow states and the timers are defined very accurately to optimize the performance.
Mm-hmm. So one just follow-up question is, so for example, this add-on miss kind of new extern or functionality is a part of Dash or is a part of P4 architecture? I mean, the PNA architecture.
I would say it is both, which is the best part here is that P4 has defined this and it's really a requirement for the edge use case that we're trying to handle. And Dash also is defining the SI APIs to define those use cases. And they, we see this marriage between what is required from Dash and to make the edge use case happen, and it can be implemented in P4 using this construct.
I see, makes sense. And another related question I had was, is P4 necessary for using Dash or are they orthogonal thing?
Yeah, the backend devices need not be P4 capable. It helps if it is P4 programmable. And especially in cases like a smart switch where we have multiple different types of components coming together, which is network processing unit and IPU, and the rich handling of how a large number of tables can be, flow tables can be handled using a SmartNIC, using all these new constructs. If they are both sort of P4 programmable, it's easier to build a device that works much more in unison. But Dash itself does not require an end device to be P4 compliant.
Makes sense. And since you just mentioned like smart switch, so in the slide, like you mentioned smart switch. So could you explain what you mean by smart switch and what are the key use cases of it?
Sure. This is a new device that is being talked about in the industry right now. And it conforms to what is required from the Dash standpoint. If we look at the cloud infrastructure and the existing racks with all the servers, and if you would like to augment that with a powerful device like this, it seems like the smart switch assumes the role of a Tor because of the place in the network. At the same time, it has all multiple IPUs, DPUs inside of this device that handle millions of flows each, and that can be SDN programmed as well. And so it just offloads and offloads the functionality of the server and manages millions and millions of flows in an optimal way together in one device, which augments the existing infrastructure.
I see. So can I think a switch, I mean, the smart switch is a kind of a combination of, for example, Tofino switch and the IPU-based smart NICs. Okay, I see.
Exactly that, exactly.
Yeah. And I guess that this is a question for Chris, probably. So in slide 14, you mentioned briefly about the conformance testing. So could you elaborate on how it would work in the context of the Dash testing framework you describe in the later slide? So for example, what will be the input and output of the conformance testing?
Sure. There's really two aspects to the conformance testing. But what conformance testing in general means is you have an API, you have a behavioral contract of how the device works. You want to exercise it thoroughly and verify the API works completely, to its full extent with every parameter verified, every corner case verified, ranges tested. And not only are you exercising the API, even just as a software test, you want to verify that the device is behaving the way it should with each set of inputs. So, for example, the SI API might feature several tables to be programmed with their attributes and values. So you'll check every value, every combination, the size of the table. So it's kind of like an exhaustive audit of the contract of the device, not necessarily under performance conditions, but actually performance is involved to some extent because some of the programmability might be a timer value, which means you have to test it in real time under performance conditions. So there's kind of two aspects. Although a lot of times performance testing means throw as many packets as you can at it and see where it breaks. That would be a simple layman's explanation of performance testing. Conformance testing is more like a thorough audit of everything. And while you're programming it, you have to send packets at it to verify that it does what it's supposed to when you've configured it with all those values. And it may mean it transforms a packet, it sends a packet, it drops a packet. So every combination needs to be tested. And of course, you can't test infinite permutations. So you have to be selective and clever about it to get the most bang for buck. And you do it in an incremental way. First, you test known use cases that you immediately want to check and make sure that it's doing what you intended. Then you start trying to break it and test corner cases and fuzzed values, etc. So it's an incremental, but ultimately it's an exhaustive process. Does that answer your question?
Yeah, definitely. Yeah, that makes sense. Yeah, thanks for your answer, both Chris and Reshma. And yeah, that's pretty much it.
Thank you very much.
Thank you.